Okay, looks like everybody's seated and ready for the second half of this session here today. I first want to thank everybody for coming out on a Saturday to sit through a session on energy efficiency and to learn more what we can do. One of the biggest reasons we do this is that the electric industry right now is really under attack, which you probably have heard through the news with the EPA. There's a big war on coal-fired power plants, and here in Michigan, that's where we get the majority of our energy. And the cost of energy based on the new emissions controls, basically most of these plants are going to have to shut down, or it's going to take billions of dollars to upgrade them to the new standard. So we can expect that over the next few years, and for quite a long time, if things remain the same, that our electric rates are going to continue to rise. And the best way to deal with that is to make sure that we don't waste any energy and that we use energy most efficiently as we can so that we use less of it so that our bill stays the same. Even though the rate is going up per kilowatt hour, we're using less kilowatt hours, and so it's not a big impact on us. So this is why we're here, is to help you manage your bills the best way you can and learn about all of the things you can do through the energy optimization programs, like we talked about earlier, and now with the heating and cooling system. This is going to be the biggest part of your bill. We live here in Michigan, and heating, when you look at the entire usage, and I've got a pie chart here coming up, so I won't spoil everything for you, but heating is your single biggest user of energy here in Michigan. Now, if you lived in Florida, we would be talking cooling. Cooling would be the biggest, and then after that it comes with your water heating and et cetera. So anyway, this is where all your energy is being spent. This is where you have the biggest bang for your buck to do something about it on a long-term basis, because the equipment we're talking about here, for instance, so geothermal, lasts 25 years or more. The high-efficiency furnaces they have today, it used to be a furnace had a 10-year life. Because of just the way the heat exchangers were breaking down. Now they've extended that out into 18 to 20 years. Outdoor air conditioners used to maybe last 8 to 10. The life of those, the way they're building them today, lasts longer. So once you put one of these in, it's going to be there for a very long time, and it's going to save you money month over month. So it's a very important aspect to look at. So again, Art Thayer, I'm the Director of Energy Efficiency Programs with the Michigan Electric Co-op Association. I'm not going to spend a lot of time boring you over my history, but I've been in the energy industry for well over 30 years. I started out at the Midland Nuclear Power Plant with Bechtel International. I was a lead discipline cost engineer out there. And when that got canceled, then I went to work for Consumers Energy in their Energy and Research and Evaluation Department. And this is where I really learned the most about energy, because it was part of my job to research it on a daily basis. From there, I moved into a position as a sales manager for all of Michigan, including the UP, for a major manufacturer of geothermal heating and cooling systems. I worked there for 10 years, and now I've been with the Michigan Electric Co-op Association for a little over 6 years. And I was brought into the association to assist with that Public Act 295 with those energy optimization programs. We're going to watch a little short video here first. We're going to pause it. This video is going to go through pretty much everything at a high level. It's very short, but it's very, very educational. And then I'll go into a little more detail as to what was in that video and why we have some of that different stuff that's explained here.
Because the Earth absorbs and stores much of the energy it receives from the sun as heat, underground temperatures remain constant at a point between 42 and 80 degrees Fahrenheit year-round, depending on where you are in the United States. A geoexchange system can use this energy source to economically heat and cool almost any kind of building, heat water, provide refrigeration, and perform many other kinds of applications. A geoexchange system is made up of 3 components: a heat pump, usually located inside the building where it's protected from the environment and vandalism; an underground heat exchanger to act as a heat sink to store energy in the earth when cooling; and to extract energy from the earth when heating. And a distribution system, such as air ducts or hydronic radiant floor tubing, to provide comfort control for the building space. The two types of heat exchangers commonly used are open loop and closed loop. A closed loop system uses a system of continuous underground pipe loops in which both ends of the pipe system are connected to the heat pump, thereby forming a sealed closed loop. Water, or a mixture of water and environmentally friendly antifreeze, circulates through the loop to transfer heat between the heat pump and the earth. In some installations, the pipes of a closed-loop system can be placed in a horizontal trench dug below the frost line. The number of pipes in each trench and the number of trenches needed will vary depending on the size of the Geoexchange system being installed and the type of soil found in the area. To minimize trenching, slinky coils, spring-like coils of polyethylene pipe, can often be used to increase the pipe surface area and thus the heat exchange per foot of trench. Another way to increase the heat exchange rate of a closed-loop system is to take advantage of the naturally higher heat transfer capability of water over soil or rock. If a stream, river, or pond of sufficient size is available, coils of heat exchanger pipe can be installed on or near the bottom to form a pond loop system. In locations where space is limited or a large heat exchanger is required, the pipes of a closed-loop geoexchange system can be installed vertically in wells drilled into the earth. As with the horizontal and pond loop systems, the number of loops and the depth of the wells needed in a vertical closed-loop system are determined by the size of the building, system demands, the ground temperature, and other variables. Since it's not necessary for the heat exchanger to be connected to the rest of the system above ground, whichever type is installed can be placed within existing landscaping, under sidewalks, driveways, and parking lots, or even beneath the building itself. In an open-loop system, on the other hand, groundwater from an aquifer is pumped through one well and passes through the heat pump where heat is added to or extracted from it. The water is then discharged back to an aquifer or harnessed for other water management uses. Because the system's water supply and discharge are not connected underground, the loop is open. To learn more about Geoexchange technology, contact the Geothermal Heat Pump Consortium at 1-888-ALL4GEO. That's 1-888-255-4436, or log on to our website at www.geoexchange.org.
All right, so what is geothermal really? Well, geothermal is really a solar system, because what it's doing is with those pipes that we talked about in the video there that we're putting in the earth, the sun's energy is absorbed in the earth every day. In fact, about 50% of the sun's energy is absorbed in the earth every day. Much of it's either absorbed in the atmosphere or reflected from the earth, but half of the sun's energy every day is absorbed in the earth. That is energy that sits right below our feet. So when we look at this, it varies on where we're at, but we can see where we're at. The ground temperature runs about 47 degrees year-round. There's a lot of heat in 47 degrees. There's heat in anything above absolute zero, and absolute zero is minus 570 some degrees. And so when we look down in Florida, we got tons of heat down there, 72 degrees. But we've got a technology, and I'll explain that. We can actually extract that heat that's in there in that 47 degrees and get that into your house. So what happens is that we use a little bit of electricity to extract that heat. And what we have is we have a compressor, we have a recirculating pump, and we either, if it's radiant inflow, we have another water pump to do that, or most cases we have forced air systems, so we've got a blower motor. Those three things are the amount of things that we need to get that energy, that sun's energy, out of the earth. So we've got this energy, a little bit of this electricity to move, get this heat to move. The second law of thermodynamics says that heat moves to where there is no heat. So if I can cause a temperature differential, I can start playing with this heat and I can get it to move whichever direction I want it to go. And by doing that, I can extract 3 units of energy out of the ground. The 1 unit of electric energy is also going to heat. That equals 4 units of heat for every 1 unit of input that we have. So that means it's 400% efficient, okay? And with newer technologies today, with inverter drives and things, and I don't want to get too technical on that stuff, but we're actually on some units getting up into the 600% efficient. This is amazing. There is no other technology out there in the entire world that is more than 100% efficient other than the heat pumps. We've got air source heat pumps, we'll talk about that, ground source heat pumps. But everything else that combust fuel, propane, wood, fuel oil, natural gas, it's less than 100% because we've got to off-gas the pollution that we create by burning that. And when we push that pollution outside, that is the less than the 100%. It used to be that a 78% furnace was considered very efficient, and it was the minimum established by law. Then it moved into the 80s, now it's into the 90s. We're actually seeing some gas furnaces now into the high 90s, 96, 97, 98%. But we'll never get over 100, where we've got with this. So you think about, you spend one thing, you get 4 things back. Isn't that great? Now let me say that, for instance, to simplify that, I've got a gas station, right? And you pull into my inefficient gas station, okay? And you tell me to put in $5 of gas, okay? And you've got an 80%. I've got this 80% efficient gas station, right? So you tell me to put in, well, actually, let's do gallons. It's easier. You tell me to pump in 5 gallons, I pump in 4, and I dump the 5th one on the ground. That's what we're doing with our propane furnaces because we're buying that gas, we're burning the gas, and then we're just dumping the rest out in the air, right? That's what 80% means. It means you lost 20%. You paid for it. You had the guy deliver it, put it in your tank, but by the time you used it, you wasted 20% and threw it out there in the air. All right? Now think about a 400% efficient gas station. That's across the street now. So you decide, you know, I don't like that idea. This guy keeps, you know, for every 5 gallons I ask for, and he dumps the last one on the ground. This is crazy. It's polluting the environment and it's wasting my money. So now you're wasting energy, right? That's very clear. You see it. In the home, we don't see it. We don't think about it. What we don't see, we don't think. But that's what you're doing with your furnaces. You go across the street to the 400 efficient gas station, right? You say, pump in 5 gallons. Give me 5 gallons. And so you give him 5, he goes for 5 and he pumps in 20 for the same amount. You know, it's 400% efficient. He's giving you 4 times what you've asked for. So your 5 gallons is now 20 gallons and nothing's on the ground. And the guy across the street's just putting in 4 and dumping the other one on the ground. Where are you going to buy gas from there on once you know what's actually going on? All right, is anybody going to go back to that 80% efficient gas station? No. Well, that's where we're at today, right? Most of us, you raised your hand, propane, right? You're less than 100%. You're probably around 80. If you've got a new one, maybe 85 or 90. If you've got a brand new one, probably 92 to 96. But still, you're paying for stuff that you're not using. So this is what the efficiency is. And I've already just gone ahead of myself because here we are with those fossil fuel furnaces. That's what propane and fuel oil and natural gas is. It's called fossil fuels. And you waste 5 to 20% in venting, which then equates to less than 100%. So when you look at this, this is a cross-section of just a very small 40-foot wide by 100-foot deep lot in the city. And if you go down 150 feet and you take a look at that cubic block of earth, there is the equivalent of 300,000 kilowatt hours in that earth that you're walking across. Did you ever think about that when you're mowing your grass and you're saying, I got 300,000 kilowatt hours right below my feet. What am I going to do with that stuff? You know, well, now you know what to do with it. So to say that a little differently, on the left is our 400% geothermal heating and cooling system. On the next one, we've got a 200% air source heat pump. Okay, we'll explain why there's differences there, but still, if you don't go with the geothermal, the next thing you ought to do is air source. And now technologies on both of these are increasing efficiencies, and it's pretty much proportional. This is an older slide. So your electric resistance heat is 100%. You get if you pay $1 for it, you get $1's worth of energy out of it. Okay. But still, that's only 1/4 as efficient as the 400% geothermal system. And then your natural gas, because we're burning, you see these three on the left, we're not burning any fossil fuel on site. So they're 100% or more. Now you get into the natural gas, the fuel oil and things. And if you still got a gas a furnace with a standing pilot in there, which many of us do. I know I have a water heater with still a standing pilot in there. That pilot is 24 hours a day, 7 days a week, 52 weeks out of the year. It's burning your propane or your fuel or your natural gas, just waiting. What do you have that thing running for in the summertime? You're not using your heat in the summertime, right? But you're still wasting that. This is wasted energy. And if you ever listen to Governor Snyder on one of his key objectives, if you ever see the State of the State address, this is what he says. He wants to reduce energy waste. And those are the types of things we waste energy. We don't even think about it. It's just sitting there wasting energy every day. And you're paying for it. So here's that pie chart I was talking about. This is what your house looks like here in Michigan. When you look at your total energy, you've got heating and cooling accounts for about 64%, hot water is about 22%, appliances are 11%, and lighting is 3%, okay? So even though we're doing a good job with our CFLs and our LEDs, we're really nibbling at a very small part of that pie. What we're here today in the second half talking about heating and cooling, this is the biggest thing you can do. And with geothermal heating and cooling, it actually picks up that hot water as well, because it's moving heat. It'll take that heat and move it into your hot water. Heating, air conditioning, hot water. That's 85% or more of our energy here in Michigan. That's what we want to deal with and try to fix here today. With the geothermal system, 50% of that is free. It's that stuff that's absorbed in the earth every single day that we've figured out how to get it in and use it. And there's no meter on that. Great Lakes Energy isn't charging you for that. Consumers Energy isn't. The propane company is. This is. So how does that work? Well, the video did that, I think, pretty well. What we're doing is we're circulating water through a system, and because of the second law of thermodynamics, we've got a process that uses refrigerant. And why do we use refrigerant? Refrigerant's been around for over 100 years. We've had refrigerators for a very, very long time. It's the same technology. How is it that you take that warm meatloaf off the stove, you put it in the refrigerator, and the next morning it's nice and cool? What happened to that heat? Well, there's a refrigerant in there, there's a compressor, there's an evaporator, and what happens is that by messing with this refrigerant, we can get heat to move. And why is that? Well, because refrigerant's highly unstable, and I hope I'm not getting in too deep in the woods here, but I know a lot of times people say, how does that geothermal system work? And you go, I have no clue. I just know that I'm saving a ton of money on my energy, I'm more comfortable, and it's doing what I want it to do, but I have no idea how this thing works. So refrigerant's highly unstable. If you compress it, it gets really hot. If you expand it, it gets really cold. Okay? We have got cold water now. We're exposing this to the cold refrigerant, which is typically around 0 degrees or so, and we circulate it through the heat exchanger, the water through this heat exchanger that takes the water, takes the heat out, because we've got 0 degree refrigerant, we've got warmer air, because we've got the warmer air that we're bringing in through here. We take the heat out of, or we take the cold out of it, actually, and we bring the heat back in. So by having cold refrigerant exposed to that 48 to 50 degree water, the heat moves from that water, or from the ground, into that refrigerant, right? Because the refrigerant's colder, the water's warmer, heat moves to where there is no heat. So now we've grabbed the heat, it's been absorbed into that refrigerant, we move that away, and then we compress it. And when we compress it, it gets really hot, maybe 150 degrees. So what happens then is, now that we've got the heat into the refrigerant, we compress that to a higher temperature. We put that through an air coil with a blower motor, and we blow that cool air through that hot air coil, and the air then absorbs, the cooler air absorbs the heat from that refrigerant, and voila, it goes from the earth to the water, to the water, to the refrigerant, to the refrigerant, to the air. Isn't that neat? And now we've heated the air. In the cooling cycle, we have what's called a reversing valve. We just reverse the process. So instead of the hot gas up in that air coil, now we're putting the cold refrigerant, that 0 degree refrigerant. We're blowing that warm, moist air across that air coil. Now the refrigerant is now absorbed that heat from the air, so it comes out of the system nice and cold. And then we take that through, and now we expand that into a hot gas. And now it's hot, 150 degrees, and we're circulating that through a 50-degree water. And now the heat goes from the air to the refrigerant, from the refrigerant to the water, from the water to the earth. So now basically what we've done, and all of that is we've gone back and forth, back and forth. In the heating cycle, we took it out of the earth, put it in your home. In the summer, we're taking it out of the home, we're putting it right back where it came from, okay? Back and forth, back and forth. No combustion, no fuel, no chimneys, no pollution, no carbon monoxide, no worrying about the heat exchanger and you go to sleep thinking you have the flu and you don't wake up, no gas explosions that you hear. Every fall you hear it, just one or two of them, you know, it's not a lot, but it's like, why do we do that, you know? Why? Well, anyway, this is a way to fix all that and to be really efficient. So next we're going to talk about loops. We have different loops. We've got about 4 different types of loops that we put in, okay? And you're wondering, why do we have 4 different types of loops? Well, the reason we have these different loops is everybody has a different situation. Somebody might be sitting on a ton of land, and we got all kinds of ground to work with, so we can put in what's called a horizontal closed loop system. And that's where we dig trenches in the ground, and we bury the pipe in through there because you got all this area to work with, right? So that makes a lot of sense. That's the most common. So we bury these trenches, right? We dig these trenches, and that's where we're recirculating the water through. We bring it into the unit, and the unit sits indoors. Or some manufacturers actually make an outdoor unit if you don't have room inside to do that. So we've got this here. We've got a lot of land out here. So what kind of land do you need? Usually that loop's 150 to 230 feet long, depending on soil conditions. If you've got a heavy damp clay, that's a really good soil that's easy to work with. If you've got a dry sand, it's harder to work with. We can still do it, but we can use a lot more pipe to get the same amount of BTUs out of there. So these trenches typically are 2 to 3 feet wide, 4 to 6 feet deep. And typically in that type of a configuration, there's 600 feet of pipe in that trench. These trenches are 10 feet apart from each other. Now, why are they 4 to 6 feet deep? Because once we get 4 to 6 feet deep, we've got all the heat we need to play with. A lot of people say, well, if I go to 12 feet, do I get more? Is it better? No, it's not. You just paid a lot more money for that backhoe to dig a lot deeper. It's going to be a lot harder to backfill, so it's cost you a lot more, and you didn't get anything for it. They've done studies here in Michigan that you've actually got to get down to around 400 to 500 feet before you really see a significant difference in ground temperature. 10 feet apart. Why 10 feet apart? Remember, we're moving heat. We're taking heat out of the earth, putting it into the house. If we have loops too close together, it's like putting 2 siblings too close together in the back seat of the car. They start fighting with each other. So again, 10 feet away from the buildings and the wells and the septic. Why? Again, if I put a loop too close to the basement, and people have asked me that, said, you know, there's heat that goes out from my basement into your, how about I snugger right up next to the basement and take that? All right, what sense does that make? I'm taking from the basement the heat that I'm turning around and putting right back into the basement, right? So we want to make sure we get far enough away so that we actually aren't stealing the energy from the building that we're actually putting the energy into. So 10 feet's a proper distance for that. Each one of these configurations is about 12,000 BTUs. So what does that mean? Here, probably the average system, correct me if I'm wrong, is about a 4-ton geothermal system up here. Yeah, 3 to 4, right? On our average size home. So 4-ton system, that means you're going to have 4 of those trenches. You've got 10 feet apart, 4 of those trenches, so you've got at least 40 feet that way, and you've got anywhere from 150 to 230 feet long, depending where that's at. You take a look at 230, and you're saying, you know what, I don't have that. What do I do now? Well, that's why we've got 4 different types of loops. This is probably the most common in the closed loop system. Okay, well now there's another way. This hadn't been very common in Michigan, but there's more and more dealers doing something along this line. This is called a Slinky Loop. And what it did is you remember we laid out the pipe horizontally, and it was 150 to 230 feet. But you're looking at it and you're saying, you know, I got the 40 feet this way, I just can't do 200 feet, but I can do 160, okay? Well, this is a way to get that pipe in the ground to get the BTUs out of there and shorten up the loop. Because now you can see we're standing it on edge and we're kind of looping things over each other. It's not as efficient as far as the amount of pipe, because here, these little cross sections right here, you're losing the heat transfer right here, but you're making up for that in the extra pipe. And pipe in the whole scheme of things is cheaper than, you know, the extra footage of pipe or the alternative on the next slide, what we do here. So simply, it's the same thing. We still get 12,000 BTUs out per trench, and it's just an amount of pipe. Okay, we need shorter pipe. We need a different way to do it because we have a smaller lot. Okay, and then as lots get even smaller, well, here's a big one. This is a Slinky Loop. Now you can do it vertically, or you can do what's called a pit installation. This is a very large project on a mountain side, as you can see the mountains there. And they put all of these Slinkies in here, and then they fill that pit back in, and that does a whole lot of work for the building. That's a huge loop. Now, you can do directional bore. Now, what is directional bore? Well, what they do is they've got these machines. You've probably seen them along the side of the highway and stuff. They do smaller gas mains in there. The phone company can bury cable in there, and they use this directional bore. What they do is they take these pipes, they push it through the ground. They've got a neat little bit that looks like a platypus bill. It's got a little angle on it. And if they want the pipe to go down, they turn the platypus bill like that, and when they shove it, the pipe keeps going deeper and deeper. When they get to the depth they want, then they start spinning that and pushing it, then it levels out. And then when they want it to come up over here, after about 230 feet or so, or how much they need, in this case it was 230 feet, they turn that bill up, they push it, and then this bill pops out. And then what they do is they've got the two ends of the pipe there, and these little stainless steel things there that are on the end of the pipe before that hooks to that. You remember these little paper Chinese handcuffs as kids? You stick your fingers in there and you can't pull them apart. That's exactly what that is, but it's made out of stainless steel. You stick the ends of the pipe in there, and then as they pull that, it's just like those Chinese handcuffs. They're going to pull all that pipe back through and into this area up here. Okay, so they just sewed that pipe in there, and guess what? Next slide here. This is the front yard. This is my house, by the way. So no trenches, right? This is before they pulled it through. They've got it laid out. This guy here actually has a machine that's monitoring that bit to let the operator know how deep it is and to let him know to quit rotating. And it feeds back to the operator there. And then, of course, he knows when to bring it back up. Okay, now, there's another way. We talked about closed loop systems. We can also do an open loop. How many people live out in the country and have well water? Okay. We can use your existing well, provided that it's big enough and that it has good quality water. And up here you usually have a lot of good quality water. When you get down into the Flint, Lapeer area, Monroe area, it is nasty. You cannot do, it's just, it clogs up, there's too much iron, there's too much other stuff in there that clogs up this heat exchanger, and the maintenance to keep that clean is crazy. They have to go with closed loop. Up here, once we get to Houghton Lake North, we can do, in fact, I think still to this day, there's more open loops from Houghton Lake North than there are closed loops. But when you get south of that, almost everything is closed loop. Okay, so here you usually need a 4 or 6 inch well that produces 15 to 30 gallons per minute. Okay, it needs to be good quality water, and the key here is you need to have a place to discharge it. That's usually a pond, a ditch, or a stream. So if you're near to a ditch, you can discharge it in a ditch, or if there's a lake or a pond or something, you can do that. Rule number 1, don't discharge it into your neighbor's yard. We had a contractor early on, this is back in the 80s, that actually did that in the Lapeer area. And they had no place to discharge it. There wasn't any ditch nearby, there wasn't any pond or anything. So they just discharged it to the ground next door, and so the next door neighbor has all this water in his backyard, can't use it. Ended up into a nasty lawsuit, and he had done so many, actually the township outlawed open loop systems because they didn't understand it, that it was just a contractor doing something he wasn't supposed to do. But so you need these things. So if you can do that, that saves a bunch of money on the installation. It's just as efficient, because that water coming out of that well is the same as the ground temperature. It's just as efficient, and it can save you some money. It can save you a lot of money, actually, on installation. If you don't have a well, then of course you could put one in, and it's the same thing. That's the well drilling rig. You see that today. You got to have this nasty, ugly little thing sticking up over there. And that one's a familiar one to me because that's my backyard over at the office. I have a Centennial Farmhouse that I have my office in. That's a long story, and I won't digress to that. This is, because isn't this a beautiful picture? No. That's the Centennial Farmhouse. So you can see that is an old, dingy basement. This is where the well already comes in, all right? You can see here's the pressure tank, which was already there. We tee off up here in the water that's already in there, so we didn't have to do anything outdoors. We just tee into that. What we have then is we tie into the unit. The unit, I don't know, did you remember that little white box that was sitting there? Here's the unit. Now this is a neat thing too. All right, so here's this old dingy basement. We're using the existing well. We're using the plumbing inside, just teeing off. We're coming out over here. We're coming down. That is the geothermal system right there, the little white box. This is what's called a split. Okay, this house has a fuel oil furnace. You can add geothermal to an existing furnace if your furnace is good. Why rip out something that's perfectly good? I'm a big believer of, hey, if you've got a lot of useful life on that, well, why am I going to rip that out just to replace it with something else that's doing the same thing? So we've got a good blower in that furnace. We've got some good parts in there. So why don't I use that for like a second or a third stage, so that if things get really, really cold, I still got that furnace there that can kick on extremely cold and windy days. And because this is a Centennial Farmhouse, a windy day makes a big difference to me because the wind like kind of goes right through that thing. So this is over here. We've got, try not to shut this thing off again. This is the water line coming in. Okay, this is the water line coming out and being discharged to a ditch, and I'll show you that. These are the refrigerant lines now that are going to the air coil that sits over the furnace. And I'm doing all my work there now. I'm putting either the hot refrigerant over there, the cold refrigerant, and I'm using this geothermal system 95% of the time. On a rare occasion I need fuel oil, it will automatically, the thermostat knows when to go into to second stage, and it will move to burning fuel oil for a short period of time. Once the thermostat's satisfied, then it goes back to using the geothermal system. So again, just a picture of the piping, and this is just an ugly picture, but it doesn't look this way anymore, but that's when we put it in. That's the discharge that's going to the ditch, and you can kind of see where that discharge line is, because you can see where the snow is right there. That's going back up to the house. You kind of see where that warmer water is coming up there. So that was, quite frankly, that installation in total was like $5,000. Now that's going to be rock bottom pricing, because generally you're going to spend more than that, but in that case it was an easy install. So you got the open loop, you've got the vertical, you've got the closed loop horizontal, you got horizontal directional bore, you had the slinky. Now if things get really tight, you're in a subdivision, you've only got a small lot, you still want to do geothermal, well what can you do? Well, we can go straight down, all right? If we go straight down, remember we could lay them out 150 feet. They had to be 10 feet apart, right? So we needed 40 feet by 150 feet approximately up there, and you can kind of picture that. That's a lot of ground. But here, I can go 150 feet deep. They need to be 10 feet apart. So I can do in a 10 by 10 area, right, what it took me for a 40 by 150 foot area. So now, who doesn't have a 10 by 10 area to work with? Again, they do the same thing. Each well produces about 12,000 BTUs or more. It depends on how deep it is and how big the pipe gets. In commercial applications, we can actually get a whole bunch more because it's a lot bigger. So that's why we have the different loops. It all works the same way. It all gets the same result at the end of the day. They're all the same efficiency. The only difference is what you're able to do with what you have to work with. Okay? This is a commercial application where they're going in with these big wells. And as I told you, they can get as many as they want. They've got a bigger borehole, they've got bigger pipe. They actually can do hundreds of these things, and then they tie these all in together into a header pit, bring it into a pump, quite frankly now, that here's the pump. So you can see that we don't have one of these things in our house. Those things are using some serious electricity to pump all of these loops in and out through this building here. Another advantage in the commercial applications is it moves heat to where there's no heat. So you can see on the south side of this building, there's a lot of heat being absorbed into that brick. This is winter. There's no trees on, no trees on the leaves. Let's say no leaves on the trees. There's a lot of heat being absorbed into those offices that we see on this end, and those people are warm. On the other side, in the shade, they're actually losing heat through that wall, and they're cold. Well, the geothermal system knows this, and it takes the heat from the side that's warm and actually just moves it to the heat that's cold. They aren't even tapping into the energy that's in the ground. They're just using the same energy, moving it around from the building that has too much of it to the building that doesn't have enough. This is the same kind of thing like in restaurants where you're taking heat out of the kitchen and air conditioning in the kitchen, but you're heating out in the dining room, okay, or vice versa. You're doing the opposite. So you can just move back and forth between inside a building, like we have here, and we can tap into that loop. Okay. The last one's a pond loop. This one takes not everybody's got a pond. A minimum of a ½ acre in surface area, no more than 100 and 150 feet away from the structure. This is a very scientific calculation. Does anybody know why that pond has to be no more than 100 to 150 feet away from the house? If you get out there to 150 feet, we already got what we need. So if the pond's further than that, well, I already got what I need by the time I'm trying to get there. So why would I keep going to get to the pond, right? Does that make sense? So then you put these pond loops in about 10 feet down or more, but that pond has to be no less than 10 feet deep at the shallowest time of year, which is usually around now, August, September, October, before the October rains. That's about the time that the pond's at its lowest. The reason for that is if it gets any shallower, we don't have enough BTUs of water there to get it. We're going to run out of BTUs. So for instance, if we're in heating, like we are in the wintertime, so it's cold out there anyway, and we don't have enough BTUs in this pond, then I'm going to turn that whole pond into ice. So this is a very big pond loop. This is a senior center here, retirement home, and all of these right here are the coils that they're going to float out here, and then when they fill those with fluid, they sink down to the bottom of the pond. And these loops right here satisfy all of that building right there. Isn't that an amazing thing? No gas, no propane. And here's a smaller one. This is for a house, a little trench to get this out. They're going to float that out to the middle, fill it with fluid, floats down to the bottom. So you've got your directional bore. You've got, which we've talked about. Why did I just throw that one in there? I'm mystified. This is what a system usually looks like. You've got the heat pump, which actually just looks like your furnace. A lot of people say a heat pump. I'm thinking it's a pump and it's weird. But that's it. This is your return air. There's your supply air. Your air coil sitting over here. Your recirculating pump is here. And your heat exchanger is in here. This is where all the work is being done down here with your compressor. Any extra heat we have, we move over here into your hot water. In fact, we have units that can dedicated to doing hot water. If you've got a lot of hot water use, or if you're doing radiant in-floor heat, we've got units that can do a multiple of that, radiant in-floor heat and stuff, just depending on your situation, what works best. But this is a 1/5 horsepower motor that's recirculating it's a mixture of water and antifreeze that's going out into the yard and gathering all of those free energy that's absorbed in the earth every day. Which means, and Dave already went through that, ka-ching, you are saving money. Gosh darn, 2 minutes? I got 2 minutes to do this. Air source is the same darn thing, okay? I'm going to shorten this up. Air source does everything I talked about with the one exception. We're not coupling into the earth. Okay, that earth is a steady 48 to 50 degrees year round. The air, on the other hand, gets really hot in the summertime and gets really cold in the wintertime. So we're extracting heat out of the air in the wintertime to heat the house, but at times the air is so cold outside it's really hard to get that heat. Okay, so that's when we looked at that one bar chart and air source heat pumps were 200% as opposed to 400 because geothermal is 50 degrees year round with a geothermal system. How hard is it going to heat and cool a house if it's a constant 50 degrees 24 hours a day? With the air source heat pump sitting outside, it uses more energy in the winter to extract the lesser amount of energy available. And it's the same thing in the summer. Heat moves to where there is no heat, but you've got an 80-door indoor and you're trying to go to a 100-degree outdoor. The heat's looking at you and saying, I don't want to go there. You know, I'm used to going to where there is no heat. Well, you've got to force it that way. We've got the technology to do it, but it takes more energy to do that. Okay? And there's certain points and limits. It used to be years ago, back in the 80s, an outdoor air source heat pump could only probably heat to when the air temperature got to about 38 degrees outdoor air. And you think about it, well, here in Michigan, there's a lot of 38 degrees, right? Particularly up here. So then you always had to have that other system. It would be called an add-on heat pump. You added it onto your fuel oil, your propane furnace, or your natural gas furnace. You always had to have that other source because once it got to less than 38 degrees, you had to start using that. Today's technology, we're getting down into like the zeros. And I'm telling you, here in Michigan, when you get down, the days below zero are less than 3%, believe it or not. 3% of the time, is less than 0 degrees. So now the outdoor or the air source heat pump is becoming more practical and applicable here in Michigan. There's still, there's still times, and many people will still recommend that you have a different source for those days that it's 20 below, because now you've got to have something there. So, but these guys over here are the experts in deciding for you what's the best installation, what's best for you, and what's going to work best for you, and figure out what that does. So I'm not going to go through all that stuff because it just basically said the same thing. You still have the same thing, your lower operating cost, you're not burning as much of the fossil fuels, so it's cleaner. And the installation is cheaper because you don't have to do that loop. So if you're looking at heat pumps, you can look at the geothermal, and you can look at the outdoor air source heat pump. Right now, we still have a 30% renewable energy credit for geothermal heating and cooling systems. So generally speaking, on a new home, your cost for a heating and cooling system might run about $8 or $9 a square foot, and your geothermal system is going to run about $5 a square foot more, so you're up into $14 or $15 a square foot. But when you look at the difference between that gas and that geothermal system, and you add in the 30% energy tax credit, it's very close. The geothermal is right in line with that high efficiency gas furnace and outdoor electric air conditioner. However, I am not your tax accountant. There is a catch. If you did not pay that much money in taxes, you're not going to get that much money back. So that's assuming, and let's say it's a $20,000 system, you would get a $60,000 tax credit off of what you owe, or a refund if you don't owe anything, but you paid that much in over the year. And when you do that, that's money in the bank. That tax credit runs through the end of 2015. Is that correct? Anybody know? Yep, Scott. That's what I'm 2015, unless it's renewed, and we don't know that yet. But the federal government, so anyway, tons of different manufacturers up there. Like I said, they're all good. Today, there might be 1 or 2 brands that still haven't stepped up their game. These guys can tell you who they are. But all these up here are good brands, and you can find them pretty well.